So we have an application that involves a high flow rate and a low head, high value of specific speed that we saw last lecture. This happens in things like drainage and irrigation. Generally use an axial flow pump. Since this is some sort of propeller inside a casing, typically the fluid discharges through a fixed set of stator vanes, and you can also have multi-stage axial pumps, so a series of rotors and stator vanes, each increasing the flow rate as it goes through. Kind of illustrative example of that is kind of a jet engine, even though that's not a pump, it's actually a turbine, but same sort of deal. You have all these sets of blades and fans moving the fluid through the engine. So the basic concepts and definitions that we've seen over the past few lectures remain the same for my axial flow pumps. There's a few things that are different though. Basic flow characteristics differ in the axial flow pump compared to the centrifugal flow pump. For one thing, the axial flow pumps have a higher head and higher shaft power at low flow rates. The head curve is also much steeper for the axial flow pump compared to the ones for the centrifugal flow pump. This leads to larger changes with respect to flow rates. If you change the flow rate, there's going to be a much bigger change in the head in the axial flow pump compared to a centrifugal flow pump. Then except at design capacity, the efficiency of the axial flow pump is generally lower than the efficiency of the centrifugal pump. So this curve here shows a comparison between the characteristics of the centrifugal pump and the axial flow pump. So centrifugal pump, the solid lines, those are similar to curves we've seen before. Axial flow pump, the dashed lines, so those are the new guys. You can see here for the axial flow pump, the dashed lines at low flow rates, so close to the y-axis, they intersect that y-axis at a lot higher values than the solid line or centrifugal pump counterparts. So I have a higher head and higher power at low flow rates for axial flow pumps compared to the centrifugal ones. You can also see that the dash curves for power and head change a lot more. So the centrifugal pump curves are relatively flat. Horsepower, for example, starts out just under 200, ends up just over 200, whereas the axial flow pump starts off at a value above 500, then drops down below 150 near the end. So much greater changes with respect to flow rate for the axial flow pumps compared to the centrifugal pumps. And then for the efficiency curve, you can see the centrifugal pump has a fairly wide peak. If you move the flow rate off of the actual peak efficiency by only a little bit, you're not going to change the efficiency very much. Whereas the axial flow pump has a fairly narrow peak, so even a small change in the flow capacity, in the flow rate, will move you away from that peak efficiency a lot farther. So centrifugal flow pumps are good for low specific speeds. Axial flow pumps are good for high specific speeds. There's also the intermediate range between 4,000 and 9,000, where mixed flow pumps have been developed, kind of a compromise between the two. So these have both axial and radial components. So instead of centrifugal flow pumps where flow comes out purely radially, or axial flow pumps where the flow comes out purely axially, these kind of have some angle between them where the flow comes out. In general, as the specific speed increases, the angle of the vanes is going to go more towards the flow direction. So instead, if the flow is coming left and right, low specific speeds, my pump's flowing, expelling the fluid radially, and then as it gets higher and higher specific speeds, it kind of goes some combination for a mixed flow pump, and then eventually really high specific speed push straight in the same direction. So now this figure shows a comparison between centrifugal, mixed flow, and axial flow pipes and their runner vane directions. So in each case, I have flow coming in left or right. And then for the centrifugal pumps, you can see that the flow changes completely 90-degree direction. So flow's going straight out of it, up and down. And those runner vanes are at a fairly steep angle. Get into the mixed flow case, higher specific speed, and those runner vanes are at an even more steep angle, and you can see the angle of flow coming in now is at some mixed angle. It's not left and right. In the axial case, it's not up and down in the centrifugal case, but some mixed flow. And then as we get to the axial flow pumps, the vanes are completely up and down. Flow coming in is the same direction as flow going out. So the centrifugal, mixed, and axial flow pumps are great for pumping liquids. When it comes to vapors and gases though, they're not so good because they create a very large pressure difference, and that very large pressure difference can lead to compressibility effects in gases that are unwanted. So because of that, pumps generally aren't used for gases or vapors. What are used instead are fans. Fans operate at relatively low rotational speeds, 100 to a couple thousand RPM. The changes in pressure across fans are generally less than 1 psi, and at those pressures differences, generally density change is less than roughly 5%, and so density change less than 5% is pretty close to being zero, so you can pretty much still treat the fluid as being incompressible, which is what we want. So fans can also be called blowers, boosters, or exhausters, depending on where they are in the system. So at the very beginning it's a blower, in the middle is a booster, at the end it's an exhauster. A turbo machine that's used to produce a large density change or large pressure change is called a compressor. So the fans generally only have small pressure changes, less than 1 psi. If you want something to have a large pressure difference on a gas, generally dealing with a compressor. And the designs of these things can include centrifugal, axial, and mixed, just like we saw before. So the axial flow fans are also called propellers. And the performance curves are very similar to the pumps. So the shapes that we saw for the pumps, the curves look very similar. The one difference here is that for the pumps, for liquids, we generally deal with head rise or head loss. For the fans, we deal with pressure rise. Just easier to deal with, head for liquids and pressure for gases. So because of this difference of pressure to head measurements, in terms of specific speed, we don't want to have head in there anymore, we want to replace it with pressure, and so the term G times H is replaced by the term pressure over density, so those two things are dimensionally the same, and so replacing that in the specific speed, there's also a dimensional US version, using again those common units that are used for these calculations. NSD, so the dimensional version for fans, is omega in RPMs. Flow rate Q is generally measured in cubic feet per minute now for the gases, as opposed to the gallons per minute for the liquids. And then I have this pressure being measured in inches of water, believe it or not. So that is the dimensional version of the specific speed for the gases for fans. And then centrifugal fans, again the lower end of the range is where you use the centrifugal type, 2,000 to 20,000. And then the axial fans in the higher ranges, 50,000 to 200,000. So time for an example. Have a certain pump with an impeller diameter of 8 inches, has the best efficiency at a flow rate of 300 gallons per minute, producing a head of 21.9 feet, rotational speed of 1170 RPM. I want to know what happens if the rotational speed is increased to 1750 RPM. Then I also want to know if this is a centrifugal or axial flow pump. So this pump has similar characteristics to one we saw a couple lectures ago. Has a shut-off head of 25, has the head of 21.9 at 300 gallons per minute, has that same rotational rate of 1170 RPMs. So I can use the data we have from that last example, where I found that head curve was 25 minus 3.44 times 10 to the negative fifth times Q squared. This is for H in feet and Q in gallons per minute. We want to scale this to the new rotational speed, and so to scale this I need to have similarity. Need to have geometric similarity, which is actually automatically satisfied because this is the same pump, so obviously it's the same geometry. And then I need dynamic similarity, so as long as there's no cavitation, cavitation happens, that changes pressures and gases, liquids, bad stuff happens. So assuming that's not the case, I'll have dynamic similarity as long as my flow coefficients are the same. So CQ for this original case equals CQ for my new case. So for my flow coefficients to be the same, CQ1 equals CQ2. CQ is Q over omega d cubed, so Q1 over omega 1 d1 cubed is Q2 over omega 2 d2 cubed. Same pump, so same diameter, so those guys just cancel out. Solving for Q2, that's just Q1 times omega 2 over omega 1. So my best efficiency point at 300 gallons per minute in the old case was at 1170 RPM. I now scaled it up to 1750 RPM, and I get 449 gallons per minute as my new operating point for the best efficiency. I also want to know what sort of head I'm going to get at this new operating point. And so my head coefficient, again, because my flow coefficient is the same, that means my CHs are going to be the same due to the dimensional analysis. And so CH1 equals CH2, so GH1 over omega 1 squared D1 squared equals GH2 over omega 2 squared D2 squared. Again, D's are the same, so those go away. Gravity's the same, I haven't moved to Mars or anything, so gravity cancels out as well. Solving this for H2, H2 is H1 times omega 2 over omega 1 squared now. So again, at my best operating point previously, I had a head of 21.9 feet. Scale this up, 1750 over 1170 squared gives me a new head of 49 feet. So question was slightly ambiguous, just asked what happens. So I went from 300 gallons per minute and 21.9 feet to a new operating point of 449 gallons per minute and a head of 49 feet. So for part B, I want to know what type of pump this is. So to do that, we can find the specific speed. Easiest way to do that is actually in the dimensional form. So using the crazy units, NSD, omega in RPMs, Q in gallons per minute, and H in feet, which is all what we have. Just plug those numbers in that we were given originally. Omega was 1170 revolutions per minute, Q was 300 gallons per minute, and my head loss was 21.9. So plug all that in, I get a specific speed of 2,000. This is right in the range of 500 to 4,000 that we see for centrifugal pumps. So this is most likely a centrifugal pump. And if you remember the similar example we did with the similar numbers a few lectures ago, there specifically stated this was a centrifugal pump. So that's probably what this is. So a couple notes on that solution. First one is that we use the dimensional form of specific speed. That was the easy way to do it. For one thing, we didn't have to do any conversions. Second way, we knew exactly where that would fall in terms of what pumps are at what values. You could also use the dimensionless form, so the actual form of specific speed, omega root Q over GH to the 3/4 power. Doing this, we need to make sure everything is actually dimensionless, so actually have to make sure that we make all the unit cancellations. So 1170 RPM, you need to change that to radians per second, so 2 pi radians per revolution over 60 seconds per minute. The Q, 300 gallons per minute. Again, we need that in feet cubed per second. So we need 0.0134 feet cubed per gallon, 60 on the bottom, seconds per minute again. Then lucky at the bottom, not too much has to happen. G of 32.2 feet per second squared. H is already in feet, which is what we want, 21.9. This gives us a value of 0.733, which again, I don't really know what that means because all the values for the centrifugal pumps, axial pumps are all in terms of the other one. But we do know that this is related to the other one by a factor of 2,733. So if I take this guy and multiply him by 2,733, I get the 2,000 that we had before. And then from there I can make a comparison and see that it falls right in the range of centrifugal pumps. Second note is that to find the specific speed, I use the original values. So original value of omega of 1170, original value of Q of 300, original value of HA of 21.9. Could also use the new values that we found. So new values of omega of 1750, Q of 449, and H of 49. Gives me, again, that same number, 2,000, so still centrifugal pump.